So for today, we're going to talk about kinematics in one dimension, motion in one dimension. And for today's video, I'm going to show you the derivation of the famous basic kinematics equation. Okay, and we're going to solve some problems involving this formula for us to be able to solve some basic problems in one dimension, kinematics in one dimension. Okay, so we have here the three equations, of which we have a delta x is equals to x minus x naught, which is the displacement. Okay, so now we have, for the first equation, we have v final velocity is equal to v naught, which is the initial velocity plus at. Delta x is equal to the displacement is equals to v naught t, okay, where v naught is the initial velocity, t is equal to time, plus 1/2 acceleration a times time squared. Okay, and the third equation is the velocity squared, final velocity squared, is equal to v naught squared, initial velocity squared, plus 2a, okay, acceleration times the displacement. Okay, we can only use these equations if the acceleration of the body or the motion is constant. Okay, is constant. Acceleration is constant. If that is not a constant, if acceleration is changing, then definitely we cannot use this equation. But most of the physics problem in one dimension, usually the acceleration is constant. Okay, so let me just show you first. From our first equation, we're going to derive this equation. V naught plus at is equals to final velocity. So, how do we derive this? We're going to use a definition of the acceleration, of which acceleration is the change in velocity with respect to time. If I'm going to cross multiply this, we have a dt is equals to dv. If I'm going to integrate both sides, I can factor out a outside of the integral because I'm integrating with respect to t. Okay? And we have dv on the left side or on the right side. So, upon integrating this, we have a times t plus the constant of integration is equals to v. Okay? So, in order for us to really get the equation, we have to replace the value of the constant of integration. So, at a given certain condition, at time is equals to 0, v, or the final velocity, is equal only to the initial velocity. Makes sense because if an object does not have any velocity, it's at rest. Okay? So, v naught at time is equals to 0. So, we have replaced this. A multiplied by 0 plus c is equals to, we have v naught. V is replaced with v naught. So, this, we know that this would be 0. So, the value only of our c is equals to v naught. So, we can replace the value of c here in our equation, okay, in our equation as v naught. So, we have v is equals to at plus c, which is equal to v naught, or v is equals to v naught plus at. So, that's how our first equation is derived. Okay? So, for the second equation, of which the second equation is actually delta x is equals to v naught t plus 1/2 at squared. So, using the definition of velocity, velocity is a change in position with respect to time. So, if I'm going to cross multiply that, v dt is equal to dx. Okay? But, before I do anything else, from our equation 1, the final velocity v is equal to this. So, we have v naught plus at. So, if I'm going to substitute v here, that would be v naught plus at dt is equals to dx. Okay? So, if I'm going to integrate that, both sides of the equation, integrate both sides of the equation, so what will happen here is that we have the integral of v naught dt, okay, plus the integral of at dt. I distributed the integral sign, and the dt here is now equal to the integral of dx. Okay, so I can factor out v naught, integral of dt, because I'm integrating with respect to t. I can also factor out a, because that's considered as constant because I'm integrating only in terms of t. So integral of dx here. So we have v naught t plus the integral of t is t squared over 2. So we have a times t squared over 2. The constant of integration plus c is now equal to the integral of dx is simply x. So if we are going to rearrange this, we have x v naught t plus 1 half, this is the 1 half, at squared plus c. Okay? But we need, again, to find the value of c in order for us to complete the equation. So at a given initial at time is equal to 0, okay, x or the position is equal to the initial position. Okay? So, that is the same. So, what will happen here? We have x is equal to x naught. We have v naught times 0 plus 1 half a times 0 squared plus c. So, this would be obviously a 0. Obviously 0. So, c is now only equal to the initial position. Okay? Initial point. So, if I'm going to substitute back the value of c in our equation here, to complete our equation, we have x is equals to v naught t plus 1 half at squared plus x naught. Okay? And if I'm going to transpose this on the left side, so we have x minus x naught is equals to v naught t plus 1 half at squared. X minus x naught is equal to delta x. We have the equation now. Okay, we have already derived the second equation for our formula. Okay, for our third equation, b squared is equals to v naught squared plus 2a delta x. Recall that our first equation is b is equals to v naught plus at. If I'm going to get this in terms of t, okay, we have v minus v naught over a. Okay, so that's my equation 1. And I'm going to plug this equation t to our second equation, which is delta x v naught t plus 1 half at squared. Okay, I'm going to substitute the value of t here on our second equation. So what happens is that we'll be having now, okay, delta x is equal now to v naught times the time, which is v minus v naught over a, okay, plus 1 half a, what is our t again, is v minus v naught over a squared. Don't forget that this time is in terms of squared. So we have now delta x is equal to v naught v minus v naught over a. Okay, as you can see here, plus 1 half a v minus v naught. This is in terms of square. If I'm going to distribute that, okay. So we have a squared also here. That is the same. That is the same term. Okay. This is what I mean is this is equal to this. So as you can see here, the a's will cancel. So we have v naught times v minus v naught over a plus 1 half, okay, or 1 over 2a. I'm going to multiply this by 1 half now. And we are left with v minus v naught squared. And we have delta x here. Okay, so if I'm going to perform numerator times numerator, denominator times denominator, we have delta x is equals to v naught v, okay, initial velocity times v over a minus v naught squared, because v naught times v naught is v naught squared over a also, plus, okay, 1 over 2a, going to perform FOIL here. So we have to square the first, v squared, minus 2v v naught, okay, plus v naught squared. So I'm going to multiply 1 over 2a in this, okay, expanded form of this. So we have delta x is now equal to v naught v over a minus v naught squared over a plus, okay, v squared over 2a minus 2v v naught over 2a, okay. So as you can see here, the 2's would cancel, okay. And what will happen again for the last term? We have plus v naught squared over 2a. So as you can see here, we are left with v naught times v over a, or v times v naught over a. And we have also v naught v here over a. So this would cancel. V naught v over a minus v naught times v over a also. Because this is a positive, this is a negative, those would cancel. Okay? So we have delta x is equal to negative v naught squared over a plus v squared over 2a plus v naught squared over 2a. And as you can see here, if I'm going to rearrange this, negative v naught squared over a plus v naught squared over 2a plus v squared over 2a, we can simplify this too. Because this is simply second term is equal to 1/2, okay, v naught squared over a plus v squared over 2a. I factor out the 1/2 so that this term would come out, okay, v naught squared over a, so that we can simplify it with this, another first term, okay? So, you can imagine that if we let this equal to x, v naught squared over a equal to x, that would be negative x plus 1/2 x. That is a simple algebra. So, negative x plus 1/2 of x, okay? So, did you get what I mean? If we let x, v naught squared over a, so we'll be having negative x plus 1/2 x. Okay, so if we algebra this, if we perform algebra on this, so we will be having what? Negative 1, okay, plus 1/2 of x would be negative 1/2 of x, which is, so negative 1/2 of x. Let me just erase. So we have negative 1/2 of x, which is v naught squared over a, plus the remaining term here, v squared over 2a. Okay? So if I'm going to, again, distribute this, so we have negative v naught squared over 2a plus v squared over 2a. Multiplying both sides by 2a, for me to eliminate the denominator, so what will happen is that we have now 2a delta x is equal to negative v naught squared plus v squared. And if we are going to rearrange this, this would be v squared, final velocity squared. Transpose negative v naught on the left side, we have v naught, positive v naught squared plus 2a delta x. And this is now our equation, by the way. So we have just derived the three basic kinematic equation. And it is advised that we memorize it rather than derive it. So I derived it so that you can only see where it came from using some integrals and some substitutions. Okay? So now we're ready to go. We're ready to solve some problems here. Okay? So I've copy pasted it on my PowerPoint. So let's solve at least three. Okay? So an airplane accelerates down a runway at 3.2 meters per second squared for 32.8 seconds until it finally lifts off the ground. This is it, okay, rather than is. Determine the distance traveled before the takeoff. So, in solving physics problem, you have to first identify the given. Okay? So, we have a given that is acceleration. It says 3.2 meters per second squared. That's the acceleration. We have the time. We have the time 32.8 seconds. And of course, that is the given. We are asked for the distance traveled. The distance traveled is x, not delta x, because delta x is the displacement. Okay? So what will happen here is that we know the acceleration, we know the time, we are to find the x. But, of course, if you're going to really analyze the problem, the airplane starts at rest. Okay? Before it finally lifts off the ground. So, the initial velocity, even though it's not said on the problem should be taken into account that that is equal to 0. So, if we are going to use the second formula, let me just rewrite again the formulas so that you won't be lost. Okay, this is our first, this is our second, and this is our third formula. Okay, so we are asked to find for the x, okay, which is this. We have an available acceleration and time is also given, so it's best to use the second equation. So we have delta x is equals to v naught t plus 1 half at squared. Delta x is x minus x naught, of which if we are going to have a reference of our point, so our x naught from the initial position at time is equal to 0, our x naught is also equal to 0. So this should be also equal to 0. So we have v naught t plus 1 half at squared. So we are left with x. We can solve now the value of x or the distance traveled. By that we have the v naught is equal to 0 times 32.8, and that should be equal to 0 also, plus 1 half at squared. So our equation reduces now to x is equals to 1 half the a. What is the a? 3.2 meters per second squared multiplied by time squared 32.8 seconds squared. So if we're going to solve that using our calculator, the answer should be 1721.34 meter. So we have 1721.34 meters. So before it finally takes off the ground, the airplane has already traveled 1721.34 meters for 32.8 seconds. So for second example, a car starts from rest. Okay, the problem is actually saying that the initial velocity is 0 because it starts from rest. Okay, that's your clue. Okay, it accelerates uniformly over a time of 5.21 seconds for a distance of 110 meters. Determine the acceleration of the car. So again, we have to actually find or list the given. We have at rest. Okay, we have at rest. That's the initial velocity is 0. Okay, and we have a time of 5.21 seconds and a distance of 110. So a time of 5.21 seconds and a distance of 110, again 110 meters. So 110 meters. Okay, so the problem is actually asking us determine the acceleration of the car. The acceleration of the car. So again, we can use the second equation, v naught t plus 1 half at squared, wherein a time is equal to 0, okay, x naught is always equal to 0. So we have x minus 0 is equal to v naught t plus 1 half at squared, where v naught, again, is equal to 0, so this would be 0. So we have x is equal to 1 half at squared. And we are asked to find for the acceleration. Okay, we have the acceleration here. So we have 2x is equals to at squared. The acceleration upon deriving the formula, we have a is equals to 2x over t squared. Okay, so we have 2 times dx, 110 meters, over time squared, which is 5.21 seconds squared. And our answer for that is 8.1 meters per second squared. The acceleration is 8.1 meters per second squared. It's very easy, right? But sometimes hard problems in physics takes time in order for you to practice. So you must practice in order for you to solve some hard problems in physics. By the way, these are easy problems. So for number 3, last problem for this video, a bike uniformly accelerate from rest to a speed of 7.10 meters per second over a distance of 35.4 meters. Determine the acceleration of the bike. So again, it starts from rest, so our initial velocity is now 0. Okay? And from rest to a speed of 7.10 meters per second. So that means that is the final velocity, 7.10 meters per second. Okay? And a distance of 35.4 meters. So that is the x, 35.4 meters. And again, our x naught again is 0 because it does not have any, it starts from the reference itself, so 0. So we are asked what is the acceleration of the bike? So the acceleration of the bike. So as you can see here, we have given a final velocity, we are given a distance, we are given an initial velocity of 0. What is the acceleration? Notice that there is no time given. So the first equation we cannot use because it has a time in it. Okay, and we don't know the time. The second equation, v naught plus t plus 1 half at squared, has also time in it. So we cannot use this equation. Definitely we can use the third equation, which is v squared is equals to v naught squared plus 2a delta x, of which our initial velocity, it starts from rest, so it should be 0. So we have v squared is equals to 2a delta x. And upon solving here, okay, so we have v squared is equals to 2a delta x is x minus x naught, of which x naught is 0. Okay, so we have v squared is equals to 2ax only. Okay, so if we're going to solve for the acceleration here, the acceleration is equal to v squared over 2x. You can only derive the equation, isolate a. So we have a v squared, which is 7.1 squared over 2 times 35.4. Okay, so we have the answer 7.1 squared. Let me just check. Times 2 times 35.4. That is 0.712 meters per second. And that's it, guys. So I hope you learned something for today. This is kinematics in one dimension. Basic example, the derivation of the equations used in kinematics in one dimension with constant acceleration. So for the next video, I'm giving you more examples, harder examples in solving for this problem. So thank you so much for listening. This is Engineer Abat, and God bless us all.